In this series of videos, we are going to look at some of the experiments and phenomena that raise questions that eventually led scientists to discovering quantum mechanics. We will start in this video with black body radiation. So scientists were aware that the spectra of different objects broadly came in two different types. There were continuous spectra, where a hot object, like a hot metal ball, for example, would emit a broad, continuous range of wavelengths. This is what we normally think of when we think of a spectrum, like a rainbow, the light coming from the sun. The sun emits a continuous spectrum. But scientists also found that if you had isolated atoms or gases under low pressure, then instead of getting a continuous spectrum, you could instead sometimes get distinct lines. And those could be emission lines or absorption lines. Those happened at the same wavelength. You would notice an absorption line if you had a hot object and then a cold gas in front of it that absorbed some of that light. So you would see it as dark lines against a continuous background. These lines, eventually scientists realized that they were related to the elements. And in fact, they could be used to discover elements. That was, in fact, how helium was discovered. They realized that there were a set of spectral lines that they hadn't seen before on Earth. And that led to the discovery of helium. And of course, eventually they found it on Earth, but at the first noticed it in the sun. So we mentioned that hot objects emit broad, continuous distribution of wavelengths. And so here is a graph that sort of summarizes that data. So you can see the graphs for objects at three different temperatures. So as a function of wavelength, you have the spectral radiance, which you can think of as roughly intensity of the light per unit wavelength. So basically, they would measure the power per unit area emitted at, say, a wavelength of 2 micrometer. Well, when we say at a wavelength of 2 micrometer, what we really mean is in a small interval around 2 micrometer. So, plus or minus 0.01, something like that. And similarly, you would do that for, 1.9, 1.8, 1.7, and so on. And you plot that data of the intensity that you're measuring. And you get this kind of curve. So it has this rather distinctive shape. You can see a few things. One is as the temperature of the object increases, you can see that the peak wavelength, right, the wavelength corresponding to the peak shifts to the left. It is shifting to shorter and shorter wavelengths, which means higher and higher frequencies. You would also notice that the area under the curve is changing quite a lot. It's becoming much more prominent as the temperature increases. You can ignore this classical theory curve. We'll talk about that later. So these two characteristics actually could be codified into mathematical expressions. So Wien's displacement law actually gave a relation for how the peak wavelength changed. So you'd have lambda peak times the temperature in Kelvin was equal to a constant, B. So you can see that, oh, yes, as the temperature increases, lambda peak decreases. And the area under the curve is related to the total power radiated by the object across all wavelengths. And what was found, this is the Stefan-Boltzmann law, what was found was that the power radiated was equal to the area of the radiating object times sigma, which is a constant, times t to the fourth. So this explains why the area increases so dramatically as the temperature rises, because it goes as t to the fourth. So these were already experimentally known, but scientists didn't know why they were true. They were just empirical facts. So we said, okay, hot objects produce continuous spectra, but does that mean that any hot object has the same spectrum? Not quite. It does depend a little bit on the material that the object is made of. But broadly speaking, yes, you can talk about an ideal hot object. And the idealness here is that you assume the object can absorb and emit all wavelengths of light. I say light, but it's really electromagnetic radiation. You can see in this graph that the visible spectrum only accounts for a tiny portion of all the radiation emitted. There's plenty of infrared and ultraviolet light as well. So we would like to characterize the spectrum of an ideal object, like we said, that absorbs and emits all colors. So if it can absorb all colors of light, then it is black. But that means also that it can emit all colors of light. Of course, that doesn't mean that all colors are emitted equally. This is why as an object gets hotter and hotter, its color changes. So a skilled blacksmith can actually tell the temperature of metal by seeing, oh, is it red hot or is it yellow hot, and so on. And this also is reflected, for example, in the colors of stars. You have cooler red stars and then hotter yellow stars like a sun, and so on to blue stars. And again, it doesn't mean that they emit only blue light or only yellow light. It's simply a matter of, it's a combination of where does their spectrum peak, and also what are we most sensitive to, what colors are we most sensitive to, and so on. All right, so we want an ideal object, what we call a black body, that will absorb all light. So how do we make that? Well, you basically take the darkest thing that you can think of, and back then that basically corresponded to lamp black, which was essentially a type of soot that was formed from burning lamp oil. It was very dark and very good at absorbing light. But you can make the object even better. Basically, you construct a cavity. So you have this double-walled cavity, and it has a tiny little opening. So any light that goes in it will hit this little projection, and then it will bounce around. And the interior surface is coated with lamp black, that basically sooty, ashy substance. And so after a few reflections, it would be essentially entirely absorbed. So you take this double-walled sphere and you heat it up to your desired temperature. Of course, once it gets hot enough, it's still taking in some light from the outside, but it's also hot enough that it's emitting light. And so you measure the radiation coming out of this tiny aperture. The idea is the aperture is small enough that it won't affect the distribution of light inside the cavity that much. It's a little hole that allows you to take a sampling of the radiation. So you look at the light coming out of this ideal black body. All right, so we have a cavity. It's been heated up, and we know that there is light bouncing around inside. From your waves course, you know that if the system is in equilibrium, then the waves inside are going to form standing modes. So here's a one-dimensional example. You can see the various, the fundamental mode, and then the higher modes as you get to higher and higher frequencies, smaller and smaller wavelengths. All the condition is that they should be able to fit in this cavity in an integer number of half wavelengths. Now, this was a one-dimensional example. What if you have instead a two-dimensional circular type cavity? So again, you can describe the modes, but now because it's two-dimensional, you need two numbers to describe the mode that you're in. This is the fundamental, and then you have, okay, the next highest, and here's the node line down the middle, and it's two-dimensional, so you can have one this way and one this way, and so you get this type of pattern. You can have a circular node line, and so on. So this, for example, corresponds to some of the vibration patterns of a circular drumhead. And of course, our 2D example doesn't have to be circular, it can be rectangular. And again, you need two numbers to describe which mode you're in. These pictures show a variety of different modes. So we are going to consider a three-dimensional example. It's a cubical box of length L. These electromagnetic waves, these standing waves, the electric field will be proportional to e to the I k dot x, right? You know this from your waves course, where k here is the wave vector. It's the three-dimensional analog of the wave number. And it would be 2 pi n vector over L, where the n vector is nx, ny, and z, giving us the three numbers that we need to determine which mode we're in. All right, so we're going to focus on this relation with the n's and the wave vector. All right, so we have k is 2 pi n over L. And then frequency, we're going to use the Greek letter nu. We know the frequency is c over lambda, but lambda is 2 pi over the magnitude of k. So plugging that in, we have magnitude k times c over 2 pi. Put all that together with the expression for k, we have nu is equal to magnitude of n times c over L. And we have magnitude over three-dimensional vector. So we have nu is equal to c and then times this magnitude over L. As a reminder, when we measure the radiation coming out in this experiment, we can't measure it at precisely one wavelength because that's impossible. You measure in a small interval around a wavelength. And so, for example, when you say you're measuring the luminosity or the radiance at 4 times 10 to the 13 hertz, what you're really doing is measuring it in a small interval around that. So what we would like to do is find the energy density corresponding to the radiation in that small interval. So if we have nu is equal to c times magnitude of n over L, what we want to do is find first the number of modes, which is going to be n nu times d nu, and these will be the number of modes between nu and nu plus d nu. So the n here is somewhat misleading. It's, n by itself is not the number, it's the number per unit wavelength. So then you have number per unit wavelength times small wavelength interval d nu, and so then this totally gives you the number of modes. And if we combine the number of modes with the energy per mode, then we'll be able to figure out the energy density of the blackbody radiation, and eventually relate that to this intensity that we're seeing coming out of the blackbody. All right, so we can rewrite that relation we have to be magnitude of n squared is L nu over c the whole square. So this is the equation for the surface of a sphere. right? Three-dimensional sphere, but you take the surface, so just a two-dimensional surface. But we are interested only in integer values of nx, ny, nz. So what we're really looking for are integer solutions to this equation, right? Given a value of nu, given a particular frequency, we want integer solutions nx, ny, nz. And what's more, we said that because it's impossible to measure at exactly one frequency, we look for the intensity in an interval between nu and nu plus d nu. So what we want are the number of solutions that lie in that interval. So what we want are the number of integer lattice points on or between two spheres, one with radius L nu over c and the other with radius L times nu plus d nu over c. Since we have nx, ny, and z, and they only take integer values, you can imagine this sort of integer 3D lattice, where each point here represents a set of nx, ny, and z. All right, so that's a little confusing. So let's look at a simpler two-dimensional example first. So if it's a two-dimensional example where you only need nx and ny to specify your mode, then you're looking at integer lattice points on a plane. And instead of looking at spheres, you're looking at circles. So what we want are the integer lattice points between two circles with very similar radii. So that would look something like this. So you have, this is one circle, this is another circle, and you're looking for, okay, how many integer points lie on or between these two circles. So on the face of it, that seems like, oh, wow, this is some really hard math. How do we, because we have square lattice and a sphere. It feels like it's going to be really complicated. But we're aided by a really fun fact, which is that the average area per lattice point is just 1. Now, okay, what does that mean? So let's say you take a square lattice and then you draw a square, right? So let's draw this square. So the total area enclosed here is 4, right? Each little square here has an area of 1. So 1, 2, 3, 4, the total area of 4. And how many lattice points are included in this square? Well, we have this one lattice point, but we also have a half lattice point here, another one half here, another half here, another half here. So that's 4 halves. So that's 2. So 2 plus this central one, so 3. And then you have 4 quarter lattice points, right? So 4 quarters is 1. So you have 3 plus 1. You have 4 lattice points included in the square and an area of 4. So the area per lattice point is 1. In fact, I didn't need to take this large square. I could have just taken this smaller one, and I could have said, okay, the area is 1, and there are 4 quarter lattice points for a total lattice point of 1. So the area per lattice point is 1. Similarly, in 3D, instead of area, we're just looking at volume. So the volume per integer lattice point is 1. So to find the number of lattice points between the two spheres, all we really need is the volume of that spherical shell between the two spheres. So what we had was one sphere of radius r, let's say, and one sphere of radius r plus dr. The volume of that shell for really tiny dr would be just like 4 pi r squared times that thickness dr. So the number of modes between nu and d nu is going to be given by 4 pi n squared times dn. And we already know that n is related to nu through this relation. And we can put all together, but there's one more thing to keep in mind, which is these are electromagnetic waves, which means there are technically 2 modes for each set of nx, ny, and z, because there are 2 different polarizations that light can have. If you're thinking circular polarizations, you can think like left-handed and right-handed, or you can think in linear polarizations, vertical and horizontal. Any other polarization is a combination of 2 of them. So we just have an overall extra factor of 2 here that we need to account for. And so we have that n nu d nu, which is the number of modes, is 2 times 4 pi n squared dn. And we can plug in and we get this. So this is the number of modes. Okay. And we said, okay, combine the number of modes with the energy per mode. So in 1900, Lord Rayleigh combined this result with the rule of thumb that, okay, each of those modes is like a simple harmonic oscillator, and at a temperature T, it should have an average energy of kBT. And you put this together, and what you have is, okay, the average energy per mode times the number of modes divided by the volume of the box, and that will give you the energy density in between nu and d nu. So this is the expression that Rayleigh derived. Well, he derived a similar relation. There was actually a numerical error in his derivation, and it was corrected later by James Jeans. So this is usually called the Rayleigh-Jeans formula. The correction was made in 1905, but funnily enough, this is the wrong expression. And Planck had already come up with the correct expression by then. But, you know, it takes time for people to get convinced, and it's worth going over old arguments and figuring things out. So here's the Rayleigh-Jeans expression. Now, it worked very well for low frequencies, but you can see that it has a flaw at high frequencies. As nu goes to infinity, so does this expression, so does this energy density. And it just keeps going without limit, and there was seemingly no objection to going to as high a frequency as you like, because the higher the frequency, the easier it is in a way to fit it inside the box, because it gets smaller and smaller. You can just fit it in, as long as you have an integer number of wavelengths. So this rise in the energy density to infinity, as you go to higher frequencies, it later became known as the ultraviolet catastrophe. Though that name itself actually came much later, in 1911, again, long after all this was resolved. Interestingly, even earlier, in 1896, Wien, the same guy who had come up with the displacement law, he had come up with an approximation that worked extremely well for high frequencies. And that was this expression here. But this did not match the data at low frequencies. So this was the situation in 1900. There were 2 approximations that were known, and they each worked in different ranges. So the green line here is the data. The red one is Rayleigh-Jeans. The blue one is Wien's formula. So you can see that, at high frequencies, Wien's formula works very well. The blue line merges with the green line here with the data. But it starts to deviate at low frequencies. But at low frequencies, oh, look, the data starts to match with the Rayleigh-Jeans. If you're wondering why this graph looks a bit different from the earlier ones, it's because it's plotted on a log-log scale. All right. So Planck was actually a big proponent of Wien's approximation. And he thought that Wien had already solved the problem. But in 1900, actually, that was when the improved experimental data came out for the low frequencies. And that was when they realized that, oh, okay, there is actually a significant deviation at low frequencies. And he had already spent months like trying to convince his fellow physicists that Wien's formula was good and correct. In fact, they were calling it the Wien-Planck law. And he heard about this experimental data, and he was desperately trying to come up with a solution. So he looked for a way to interpolate between the 2 approximations. And stroke of genius, he came up with something. Here's the Rayleigh-Jeans, here's Wien's law. He came up with this function that in the low frequency limit would approximate to the Rayleigh-Jeans law, and in the high frequency limit would approximate to the Wien's approximation. And here's the fun thing. It was a pure guess. he was just looking for something that would mathematically fit the bill, and he had no idea why it worked, but it worked, and it worked really well. Further experiments confirmed they really fit Planck's formula. At the time, he had no explanation for it, but it took like almost another year of hard work for him to figure it out. And in honor of him, H is now known as Planck's constant. So here again is the graph, and now you can see again those the two approximations and then Planck's law. So you can see that yes, the Rayleigh-Jeans it works at low frequencies, but like as soon as you start increasing your frequencies, it starts shooting off. That's the ultraviolet catastrophe. Yeah, as soon as you start going to high frequencies. Wien's works extremely well at high frequencies, but then starts to deviate at low frequencies. And then Planck's is, in fact, the correct answer. Yeah. So how did Planck, what solution did he come up with to justify his formula? So eventually he was led to this idea that for an oscillator of frequency nu, they couldn't absorb and emit arbitrary amounts of energy. Instead, they had to give out and accept energy in multiples of h nu. So there was this minimum amount of energy that they could absorb and emit. And this was what he called a quantum, right? So the idea of quantum here is an indivisible minimum bundle, right? A minimum amount. And it was an idea that he accepted with great reluctance, but it solved everything. It gave the correct formula, and then from Planck's formula you could derive Wien's displacement law and the Stefan-Boltzmann law, and it fit the experimental data. So he had to accept it. His original derivation is too long and complicated. Now we're going to look at a simpler derivation given by Lorentz. So in the previous video on probability, we've mentioned the Boltzmann rule. If you have a system in thermal equilibrium, what's the probability of finding it with a particular energy? So if the energy E as a function of nu is allowed to vary continuously, then your average energy per mode is going to be this integral from 0 to infinity of this, right? So this is the probability times the energy, right? And then integrated. And then divided by this normalization factor. And so then if you do this integral, you just get kBT. And so this was the classical result. And we've re-derived the result that Rayleigh used, that on average at temperature T, the average thermal energy per mode is kBT. But now, what did Planck say? Planck said, okay, you can't allow E to vary arbitrarily. Instead, E has to come in integer multiples of h nu. All right, so now we're not doing an integral. We're instead doing a summation. We're still using Boltzmann's rule, exponential minus E over kBT, but your E now is nh nu. And again, we're doing a summation, so no need for dE, but you have, okay, the probability times the energy, so times nh nu, and just summing it over, and then divide by the normalization factor. And if you do this summation and simplify, you get this expression. And this is the correct formula for the average energy per mode. And if you plug this in, we had correctly counted the number of modes. If you plug this in for the average energy per mode, you can correct Rayleigh's derivation and get the correct Planck result. And Planck successes all around us. If you go, well, even if you don't go out into space, if you measure, if you point a receiver in any direction in space, you will see that there is the cosmic microwave background radiation. So this is a relic of when the universe is very small and very hot. And of course, if it was a hot, densely packed object, then its spectrum would have followed Planck's blackbody radiation law. As the universe expanded, that radiation cooled and lengthened in wavelength until it eventually got into the microwave range, which is where we detect it now. And this is the experimental data. In this graph, you can't even see the error bars. The error bars are there, they're just too small to be seen because on the one hand, you're measuring intensities on the scale of megajanskis per steradian, but in hundreds of those, but the residual is like 1,000 times smaller. And it corresponds to the background radiation having a current temperature of 2.725 Kelvin. But it's a blackbody radiation. Interestingly, Planck ushered in the quantum revolution, but he was a reluctant revolutionary. See, he thought that radiation itself was still like a classical wave phenomena. He thought that it was sort of like butter, that butter itself comes in any quantity, but it's sold in very standard package sizes. And so he thought that, okay, it's the atoms or the oscillators in the walls of the cavity that are imposing this quantization effect. But in 1905, in order to explain the photoelectric effect, Einstein said, no, actually the radiation itself is quantized. It comes in these discrete packs. There's no choice. You can't get it in arbitrary amounts. And eventually these radiation quanta got the name photons that came from the chemist G.N. Lewis. So Einstein used this idea to explain the photoelectric effect. Planck did not like this proposal, but eventually he had to accept that it worked, and he had already started the quantum revolution. So this is Planck's constant, h. It's 6.626 times 10 to the minus 34 joule seconds. Often in this course, we will use h bar, right? So h with a little bar through the top, and that's simply h over 2 pi. And it just makes some of the formulas look nicer, that's all. Some fun stuff about Planck, some stuff from Wikipedia and the internet. Yeah, I'm not going to read it out, just leave it on the screen for a moment. You can read yourself. Here's another one about afterwards when it's no longer a student, became a professor. Lise Meitner was a very famous physicist later on. And then finally this. All right, the story continues with the photoelectric effect, but that is in the next video.